Welcome to this explainer. I am so pumped you're here today because, well, we're going on a pretty incredible journey. We're going to tackle one of the most stubborn, honestly frustrating physics problems in human history. And then we're going to look at an absolutely mind-blowing off-world solution. We are talking about building a literal gas station on the moon. Now, I know it sounds straight out of a science fiction novel, but the science, the data, and the engineering behind this are incredibly real. So what if the biggest barrier to exploring the solar system could be solved by a tent on the moon? It's a wild thought, right? We're actually going to skip the traditional agenda today because this story is just way too good to delay. We're going to jump straight into why space travel is so incredibly difficult and how a super elegant, almost unbelievably simple structure on the lunar surface is basically going to rewrite the entire future of deep space exploration. Okay, let's dive into this and meet the main villain of our story. If you've ever taken a freshman physics or engineering class, you might actually recognize this formula. It's the rocket equation, and quite frankly, it is terrifying. It basically dictates that the farther you want to go in space, meaning you have to increase your change in velocity, or delta V, the amount of propellant you need increases at an exponential rate. In the space industry, they actually call this the tyranny of the rocket equation. It's this unforgiving mathematical wall that makes leaving Earth just unbelievably costly and difficult.
To really grasp how punishing this math is, let's look at a quick comparison. Imagine you're going on a normal road trip from Washington, D.C. to Los Angeles. Normally, you just pull over and stop at gas stations along the way. Easy. But the rocket equation forces us to do the space trip version. Imagine driving from D.C. to L.A., but you have to tow every single drop of gasoline you're going to need for the entire trip, right from the very start. Your car couldn't haul it, so you'd need a truck. But wait, that truck gets worse mileage, so you need a bigger trailer, which means you need an even bigger truck. It's an endless loop. This brilliantly illustrates why historic rockets like the Saturn V or the new Space Launch System consist almost entirely of heavy, massive fuel just to escape Earth's gravity.
But here is where things get really good. Read this quote from the source material. Climbing out of the moon's gravity well compared to Earth's is analogous to climbing a tall building versus Mount Everest. I mean, what a massive relief. If we don't have to drag all our fuel out of Earth's heavy gravity well, if we can just get our gas off Earth, specifically on the moon, we completely break the tyranny of the rocket equation. Sourcing propellant in space gives us this unbelievable energy advantage, literally lowering the cost of operations in high Earth orbit by an order of magnitude.
Which brings us to this breathtaking map. This is the lunar South Pole. See those deep blue spots inside craters like Cabeus and Shoemaker? Those represent what we call permanently shadowed regions, or PSRs. Because of the shallow angle of the sun at the moon's poles, the bottoms of these deep craters haven't seen a single ray of sunlight in billions of years. They are incredibly cold, acting as literal cold traps. And what exactly are they trapping? Water, which is the exact raw material we need to create liquid hydrogen and liquid oxygen. And those just happen to be the most efficient rocket propellants we have. Now, we aren't just guessing that water is there. We know it thanks to a massive global scientific effort from missions like Clementine, the Lunar Reconnaissance Orbiter, and Ellscross, which literally impacted a spacecraft into a crater just to analyze the dust plume. And crucially, we have amazing data from the Indian Space Agency's mission Chandrayaan-1. Together, all these international precursor missions confirm that the moon is hiding vast, significant quantities of water ice right there in those permanent shadows.
And that brings us to an absolute game changer of a number, 30%. Recent analysis of the data has revealed that in some of these permanently shadowed regions, the concentration of surface water ice can be up to 30% by mass. This isn't just a few microscopic frost crystals mixed in with the dirt, you guys. This is a highly concentrated, economically viable reserve of ice just waiting to be processed into rocket fuel. It seriously changes everything.
But how do we actually get it out? Traditional earth mining uses heavy excavators, massive dump trucks, and involves tearing up the ground. If you try to send a giant caterpillar bulldozer to the moon's poles, it has to survive extreme cold, highly abrasive dust, a hard vacuum, and low gravity. Excavation approaches would just be overwhelmingly heavy and way too costly to deploy. Instead, space mining demands an elegant, sci-fi-made real solution. We don't dig, we use sublimation. We skip the heavy machinery entirely and use ultra-lightweight cold traps.
This is where we get a process called passive thermal mining, and it is incredibly efficient. It breaks down into 4 simple steps. Step 1, we capture sunlight up at the crater rim using large mirrors, called heliostats. Step 2,
That captured light is redirected down into the pitch-black crater, straight into a specialized tent. Step 3. The heat directly hits the icy lunar dirt inside, causing the ice to sublimate. Now, sublimate just means it turns directly from solid ice into water vapor without ever becoming a liquid puddle. Step 4. That vapor naturally flows into a sub-freezing collection tank known as a cold trap.
Now, what's really interesting here is seeing those exact steps in action. Just follow the yellow arrows on the diagram. You can see the concentrated sunlight coming down from the crater rim. It hits those secondary optics right at the top of our structure. That's the capture tent. The light beams straight down, heating the icy regolith. Now look at the blue arrows pointing up. That is the sublimated water vapor lifting right out of the dirt. It's trapped by the impermeable tent structure, which stops it from just venting out into the vacuum of space, and it gets funneled straight into those blue cold trap vehicles waiting on the sides.
And this is what the whole setup could actually look like. This concept art shows the sheer elegance of the capture tent sitting on the lunar surface. Notice anything missing? There is not a single shovel hitting the dirt, no spinning drill bits grinding down in the harsh lunar dust. The cold traps on those little robotic haulers utilize what engineers call variable conductance heat pipes, or VCHPs, which effectively capture and refreeze that vapor back into ice. Once a cold trap is completely full of pure ice, the hauler just detaches and drives it over to an electrolysis plant, where it's separated into hydrogen and oxygen. It is a completely passive system, relying almost entirely on redirected sunlight.
So what's the big so what here? Why does all this matter right now? Well, NASA and its international partners are currently developing the Lunar Gateway, a brand new space station in high lunar orbit. To keep the gateway supplied with logistics and life support, early plans require launching 4 commercial missions from Earth every single year. But if we can produce liquid oxygen and hydrogen right there on the moon, we can just refuel those spacecraft in orbit. By utilizing this lunar gas station, we can deliver the exact same mass to the gateway using just 2 missions a year instead of 4. It literally cuts our logistics burden in half and establishes a true, sustainable interplanetary stepping stone.
We started this explainer talking about the terrifying exponential math of the rocket equation. But by utilizing the moon's permanently shadowed craters and the sheer ingenuity of thermal mining, we can finally bypass that math, which leaves us with a pretty profound question. Once the tyranny of Earth's gravity is finally broken and our vehicles can easily fuel up in orbit, where should humanity go next? Mars, the asteroid belt, the outer edges of the solar system? The solar system essentially becomes our backyard. Think about that for a bit, and I'll see you in the next explainer.